Okay, thank you. And I thank the organizers for organizing this wonderful conference. And I'm also learning what is the p-adic Kudla program, so so it's great. So for today, the goal is to talk about, so introduce sort of one half of what is on this p-adic Eichler-Shimura isomorphism as introduced by Van Sant. So I'll talk about completed cohomology and locally analytic vectors. So let me know if the handwriting gets too small at some point. So let me recall some setup. So we're considering this situation of Shimura varieties. And so given a compact open subgroup, or a level, which we maybe assume is neat, we get a Shimura variety, which I'm going to use this kind of heavy notation, but sometimes I'll kind of relieve it a bit. And this also has this sort of toroidal compactification, which was recalled by Van Sant. And for now, we're viewing these as algebraic varieties over the reflex field, which is a finite extension of Q. Okay, so let me introduce some notation, and then I'll define what is completed cohomology. So the notation I want to use, just to sort of lighten things a little bit, is for R, one of Z mod P to the SC, ZP, or QP, I'm going to define HI K, so K is one of these levels, R, as just the cohomology of the open Shimura variety with these coefficients. And so we can either think about this as Betti cohomology of the complex points of the Shimura variety with coefficients in R, or we can think about this as sort of p-torsion or p-adic étale cohomology of the Shimura variety base change to Q bar with coefficients in R. And we'll sort of use both of these points of view. In fact, a lot of the things I say today are purely topological using this definition, and will even hold in the more general setting of arithmetic locally symmetric spaces where you don't really have this structure of an algebraic variety. But of course, the big advantage of this is that it carries a Galois action. Okay, so let me introduce the definition of completed cohomology as introduced in the introduction of Van Sant's talk. So following Emerton, we let, so maybe I'm going to let my level K be a product of Kp and K upper P, where Kp is an open compact subgroup of GQP. And K upper P, well, it's an open compact in the adelic points away from infinity and P, and this is what we call the tame level. And typically we'll just kind of fix it. So the definition is, so first with Z mod P to the SC coefficients, is that you just take co-limit over all levels Kp of the cohomology at finite level. Okay? And so we sort of call this mod P completed cohomology, but really there's nothing completed about it. It's just a sort of, this is a sort of smooth representation of GQP, because somehow the action of GQP will kind of conjugate these subgroups Kp, and then when we take the co-limit, we'll get an action of GQP on it. Okay, and then we make the similar definition, well, with ZP coefficients, where the key point is that we take the limit over S of these things. And I'll even just write it again. So it's the limit over S of the colimit over Kp of hi Kp Kp z mod p to the sc. And finally, we can define completed cohomology with rational coefficients by just taking the sort of integral one and tensoring with Qp, inverting P. Okay, and so again, I mean, this gets some kind of topology from the inverse limit, but a priori it's not completely clear what kind of topological space this or this is, but it does at least, again, carry this kind of continuous action of GQP. Not really continuous and not smooth. So I want to say a few basic things about this definition before I start explaining some of its properties, and this is especially for people who have kind of never worked with this object before. So let's make some remarks. So first of all, I mean, when we define this thing, the order of the limit really matters. So the completed cohomology with ZP coefficients is sort of much bigger than the kind of other thing where you, so maybe I'll introduce even a notation for it. I'll call it hi Kp Zp, which is just the colimit over Kp of the classical cohomologies with Zp coefficients. And if you like, that's also the limit over S of the classical cohomologies with Z mod P to the SC coefficients. So these things are finite ZP modules, and so they're already kind of p-adically complete. And so for example, I mean, this is really just a smooth representation of GQP. And so for example, like if you're working in the case of the modular curve, if you consider this object, it really only sees Hecke eigenvalues of weight 2 modular forms. Whereas what we'll explain is that this sees Hecke eigenvalues of all weight modular forms and all level modular forms, and this is justifying Emerton's idea that this is some kind of space of p-adic modular forms. Maybe something else I'll quickly explain is that there's kind of another definition of something which you might consider p-adically completed cohomology in maybe a more natural or naive sense, which is just to take the p-adic completion of this thing. And so Emerton also considers this. So what he calls hi hat, which is just the limit over S of sort of, so literally the p-adic completion of this thing. So you take this thing and you tensor with Z mod P to the SC. Okay? And I don't actually know, but I kind of, well, I'll explain something about this in a moment, but I kind of suspect that Emerton considered this definition first because he used hat for this and twiddle for this. But it turns out that in general, the twiddle one is really the better one. So let me explain quickly the relation. So the relation is, there's actually just some short exact sequences. So this kind of literal completed cohomology actually embeds into the kind of correct definition of completed cohomology. And then there's a co-kernel, and the co-kernel is the p-adic Tate module of this. And I explain what I mean by that. So by definition, this is just the limit over S, but where the transition maps are kind of multiplication by P of the P to the S torsion. So compatible systems of under multiplication by P of P to the S torsion in here. And so I'll leave this as a little exercise, but I mean, the idea to prove this is that you just look at the sort of usual kind of Bockstein, or whatever you call it, sequence. And you consider the long exact sequence of cohomology just at finite level, and you split it up, as usual, into these kind of short exact sequences that you have the cohomology So the ZP cohomology at finite level mod p to the s going to the z mod p to the s cohomology, and then that goes to the p to the s torsion in H1, hi plus 1. And now you just take this and you take kind of co-limit over kp and a limit over kp. And you just check that the three things that you get are exactly these three things. And you also have to justify that this stays exact, but I mean, this sequence, every map is surjective, so there's no R1 lim. Did I screw something? Yeah, sorry. Okay, yeah, I stated this wrong. Yeah, sorry. Sorry, I think I said the right thing, but I wrote the wrong thing. Thank you very much. And it's wrong here too. I apologize. Okay, thank you. Okay. Okay, so let's get started kind of understanding some of the properties of completed cohomology. So I want to sort of prove, or at least kind of sketch a proof of some finiteness theorems for completed cohomology and kind of explain what kind of objects they are. So we have the following proposition. So it says that, so let's say, so fix a kp inside GQP, compact open, then, so the claim is that sort of hi completed cohomology with its kp action is computed by a complex sorry, I realized I really wanted to say something. I'm really sorry. I wanted to say just one more thing about this hi hat, which is that in the case of the modular curve, H2 is 0, and so these two things are actually the same. And so sometimes when people talk about completed cohomology of the modular curve, they actually use this H1 hat definition. And that's part of the reason why I wanted to mention this at all. Sorry, I should have really said that. Okay. It's computed by a complex of the form well, I'll explain what this notation means if you can't guess, but okay? And so in some sense, this is kind of explaining what does completed cohomology look like. And so what is this thing? So CKP ZP, this is just my notation for continuous functions from KP to ZP. All right. Okay? And let me state a few more properties, which, well, I'll somewhat prove. So first of all, there's something you might wonder about this definition, which is we took a limit over S, and you could have also taken some kind of derived limit over S, and in fact, it's the same. So R1 lim hi tilde kp z mod p to the sz is 0. So in the definition of completed cohomology with ZP coefficients, I could have put an R lim there instead. And let me just say that this completed cohomology has bounded p torsion. Can have lots of p torsion, but it's bounded, and is p-adically complete. And so in particular, that implies that this QP completed cohomology is a p-adic Banach space. Let me switch. Okay, so let me sketch the proof of this. So the first thing that we want to use is that, so we fix this finite level, we fix this Kp. So we first want to use that SKP KPC has the homotopy type of a finite CW complex. And so there's a couple of ways to understand this, none of which I'm really going to explain. But for one thing, it's the C point of an algebraic variety, and it always has the homotopy type of a finite CW complex. Maybe another way to see this is by using the sort of reduction theory of arithmetic groups and the theory of the Borel-Serre compactification. But one way or the other, you see this, and now we're going to use it. So let's fix a cell decomposition. And now let's consider what we get when we go to deeper level. So if we take Kp prime normal in Kp, we get a cell decomposition of the deeper level just by pulling back. And so, well, when you do this, well, actually, so this map, sorry. Well, okay, I already switched to stop writing these. So this map, SKP KP to SKP KP, this is a KP mod KP prime cover. Well, actually, I have to admit that's not always true. It's true under some assumption on the Shimura datum, like for example, that it has Hodge-Tate, and I'm really just going to assume that for simplicity. So let's just assume that this is actually true. And so what it means is that sort of above each cell in here, the cells which kind of are in its pre-image are a torsor for this group. So a torsor and I just want to sort of trivialize this sort of compatibly for all Kp prime. Okay? And so now we get some cellular cochain complexes, and what do they look like? So let me write this as C bullet Kp prime. Well, maybe I'll include Kp. C mod p to the SC. So basically, this is just going to be a complex of Kp mod Kp prime modules, which is of the form, well, continuous, or, well, these are just functions. Valued in z mod p to the SC to some n0 and so on, okay? And so now I can take this sort of colimit, colimit over Kp, and I will get a complex m bullet of the form advertised in the statement of the proposition. So I take the colimit over Kp, so I'll just get continuous functions from Kp, or locally constant functions from Kp to z mod p to the SC, and then I take a limit. Okay? And now, what's clear is that the cohomology of this complex mod p to the s computes completed cohomology mod p to the s, because we just took a colimit of complexes which compute the cohomology at finite level. But what's not at all clear is that taking the limit commutes with taking cohomology. And in fact, I mean, proving this is basically equivalent to proving this thing that I claimed here. Okay, so we need to really do something to understand this. And so I can't do, no, I can only do one board at a time. So my 3 cycle will take a moment. Let me just make sure that this board is visible. Sorry, it turns out I'm not capable of talking and managing the boards at the same time. Maybe I'll get better at it. Okay. So what Emerton does is inspired by some earlier work of Schneider and Teitelbaum, which I'll explain a bit more about in a moment, on the theory of admissible representations. And so the idea is that it's really better to kind of consider the dual of this complex and consider homology first. So the idea is that it's better to consider homology first. And you'll see why in a moment. So we take the dual of this complex, by which I mean take sort of term-wise continuous homomorphisms from this complex into ZP. And so what does this complex look like? Well, basically, we have to understand what is the kind of dual of this space of continuous functions. But, so maybe I'll call this like N bullet, because that's what it's called in the notes. So hom from continuous functions on Kp, well, that is exactly the space of sort of p-adic measures on Kp, or the sort of Iwasawa algebra of Kp. And so that is the completed group ring of Kp, which can also be defined, and well, let me write this in a slightly weird way, but I can write this as sort of limit over S of limit over Kp. Of course, these limits now commute because they're both limits. Z mod p to the SZ, and just the finite group ring. Maybe I should take, sorry, I have a fixed Kp, so I should call this something else. And maybe I'll take it normal. Okay? So in other words, I mean, anyways, this is in some sense the same as this. It's just continuous functions on this finite group valued in Z mod PZ, or just functions, sorry, there's no continuity, except that now instead of taking the co-limit over the level, we take the limit over the level, and then we also take the limit over S. Okay? So that's the dual of the space of continuous functions. And so it means that this complex is now a complex where all the terms are just finite free modules over the Iwasawa algebra. So okay, and maybe the numbers are going in the other way now. Okay, and so the idea is that it's actually kind of better to first understand the cohomology of this complex in order to understand the cohomology of the dual complex. And why is that? And this was sort of the key idea in this work of Schneider and Teitelbaum, is that this ring it's first of all, it's a Noetherian ring, which is a theorem of Lazard, and it's also a compact topological ring, or a profinite ring. Actually, yeah. Okay, and so what that buys us is that we can kind of make the topologies go away. So the consequence is that we have an equivalence between some category of kind of topological modules over this ring with continuous maps. So compact topological ZP KP modules, which are finitely generated just in the usual commutative algebra sense. This is really equivalent to just the category of finitely generated ZPG modules. So in other words, this sort of purely algebraic category. Okay, and so why is this? Well, it's basically, what we're saying is that sort of any object here actually has to have just a canonical topology, which is determined purely algebraically, and every map is kind of automatically continuous. And so sort of, let me just say, rather than carefully prove this, what is kind of the point is that suppose you take one of these guys and you write it as a quotient. So this map, this is a surjective map of compact Hausdorff spaces. And so sorry, compact always means Hausdorff when I was saying it here. This is a surjective map of compact Hausdorff spaces. Sorry, what did I write? I don't know where C came from. Thank you. So it's a surjective map of compact Hausdorff spaces, and so this tells you that M has the quotient topology. And so in this way, you can kind of endow every object here with the kind of canonical topology, and you check that all the maps are continuous. Yeah, I'm sorry. Yeah. Okay. Okay, I have to do some permutation of the boards again. Okay, this seems smarter in my head, but is this actually the right way to do the boards in this lecture hall? I'm not totally sure. I think there's some trick where you speed it up by using your hands, but then there's some order to do it in. Okay, and okay, and anyway, so I'm not going to really explain the rest of the proof. I've kind of explained the key idea, but now this basically implies that the cohomology of this complex n bullet is very nicely behaved. So it implies that sort of are p-adically complete with bounded p-torsion. Well, in fact, because they're objects of this category, and all finitely generated modules of the Iwasawa algebra are p-adically complete with bounded p-torsion, and so dualizing gives the statements for M bullet. Okay, but I don't really explain it carefully. Okay, any questions about that? Okay, so as group cohomology, sorry, but group cohomology of what group?
Your complex looks like
But you want to now take KP cohomology, or you? Okay, I'm about to talk about taking KP cohomology, if that's what you want, but okay. Okay, so the next thing, okay, so the next thing I want to explain is sort of the relation between completed cohomology and cohomology at finite level. And so Emerton proves the following Hochschild-Serre spectral sequence. So let V be a KP module, which is finite free as a ZP module. Then there's a spectral sequence so we take continuous group cohomology of KP with coefficients in completed cohomology, the ZP coefficients tensored with V. And this computes the finite level cohomology of the local system associated to V. So, I mean, a representation of KP defines a local system on the Shimura variety at this level, and I take the cohomology of that local system. Okay. And so, well, I also am not entirely going to prove this, but let me just explain more or less what is the idea. Sorry. Ah, sorry. Yeah, you're right. Thank you. Ah, okay. I'm using a different kind of chalk now. Maybe I shouldn't use this chalk.
Yeah, so there are too many P's.
Sorry?
There are too many P's.
Sorry, but you'll never get confused. Okay? I promise. It will never confuse you. Yeah, sorry. You have to deal with that. Okay, so what is the idea? So basically, I mean, we have this nice complex which kind of computes cohomology for us. And so the idea is that what you're going to show is that sort of M-bullet tensor V, so with its kind of KP acting on both M-bullet and V, so the cohomology of this complex computes well, completed cohomology tensored with V. Well, okay, let me use I again. And you're going to use that the terms are HI continuous KP acyclic. And this is basically just because by some version of Shapiro's lemma, the space of continuous functions on KP is acyclic. And finally, if we take the cohomology of this complex, if we take the KP invariance, this computes this cohomology at finite level. And so you should believe that there is such a spectral sequence. But I emphasize that this is not really a tautology because somehow, I mean, continuous group cohomology, it's not really defined as a derived function on an abelian category. And so you really have to, or if you're Emerton, you really have to kind of check carefully that such a spectral sequence exists, using that you're in this kind of nice small category of modules that look like they're computed by complexes like M-bullet. Or alternatively, you can use something like condensed group cohomology to get this spectral sequence. But if you do that, then you have to actually check that sort of what you get kind of agrees with the usual continuous cohomology. And there's still something to prove there. Okay, so that's kind of the idea. And so this spectral sequence, it justifies Emerton's idea that completed cohomology is a space of p-adic modular forms. So for example, we could take, for the modular curve, we could take this V to be something like this space sim k zp that we considered in the first lecture, which we said has something to do with weight k plus 2 modular forms, or its cohomology. And we see that we can sort of completed cohomology, even though we sort of started with cohomology with trivial coefficients, or really just H1 in this case, sort of computes or determines this sort of finite level cohomology with coefficients in this local system. Okay? And so this justifies Emerton's idea that completed cohomology is a space of p-adic modular forms. Inside it, you'll see the Hecke eigenvalues of all modular forms of all levels at p and of all weights. Okay. No, this is supposed to go up, sorry. Oh my God. Oh no. Sorry, I've just broken the board thing at CERM. Oh no. Okay, sorry about that. I imagine it was already broken. Okay. So, okay. So the last thing I want to do is recall, well, not the last thing, but the next thing, is I want to recall this notion of admissible representations of Schneider and Teitelbaum. So the idea is, sort of definition, QP Banach representation of KP is called admissible if, so when we take the dual, or what is classically called the weak dual, but I'm just going to write HOM QP, well, I should write HOM continuous or something, but okay. So if we take the weak dual is a finitely generated module. So now we're working with p inverted, so I should say a finitely generated module over the completed group ring with p inverted. And so a basic example would be the continuous functions on Kp with values in Qp, which is exactly going to be dual to this. Okay? And so by the principle that I explained mid-proof about modules over this ring, this is somehow a purely algebraic category. So theorem of Schneider and Teitelbaum is that there's an anti-equivalence between, well, let me just call it adm Kp, so admissible representations of Kp, and finitely generated modules over this Iwasawa algebra with p inverted. Okay, and the proof is basically by the same idea that I explained for modules over this ring without p inverted. And you just pick a lattice and use the same argument. Okay, and so in particular, this category is abelian. And so the kind of thing that you might have worried about, but like maybe I have a map between representations. I mean, if I have a map between Banach spaces, it could be possible that the image is not closed, and then so the co-kernel is not separated, and all those kind of things. I don't have to worry about that in this category of admissible representations of a p-adic group. Okay, and maybe one last definition is that, so a representation, QP Banach representation of GQP is admissible its restriction to some or equivalently any KP and GQP is open compact, of course. Okay, and so, I mean, the point of introducing this definition is that, anyways, the QP completed cohomology lies in this nice category of admissible representations of GQP. Okay, so everything that I've said so far is purely topological and, oh dear, and is also holding in the kind of world of general locally symmetric spaces, and now it's time to come back to geometry. So completed cohomology was defined using the sort of open Shimura variety, and we have this compactification, which we haven't really explained precisely what it is, the toroidal compactification, but anyways, you just think about the case of the modular curve, the open modular curve, and the compactified one. And so the first thing I want to explain is that actually completed cohomology can also be computed on the toroidal compactification. So, proposition. So there's a kind of restriction map from cohomology here to cohomology here. And so the map going from lim Kp, so the thing which would be completed cohomology of this guy, sorry, let me actually not bother to, let's just work with p to the s coefficients. It'll imply the thing with zp coefficients. Is an isomorphism. Okay? And, well, already this might seem a little bit strange in the case of the modular curve because, so for the modular curve, the open modular curve has no H2, but the open modular curve has no H2, but the compactified modular curve has H2 because it's a complete curve. But then you'll see that that H2 is dying when you pass the completed cohomology because as you increase the level at P, you're getting maps on components which are degree a power of P. And so the pullback maps on this H2 will involve multiplication by P and thus kill the cohomology when you take the colimit over Kp. Okay, so let me explain why this is true just in the case of the modular curve. So, and so just to ease notation a bit, I write sort of yk inside xk for the C points of the modular curves. Oh, sorry, that's completed cohomology. Thank you. Well, actually, the way I define this, it's really the same thing, because it's just there's no completing happening, right? It's just a torsion case. But anyways, yeah. Okay. So what are we going to do? Well, there's a relative cohomology sequence. So we consider the relative cohomology of the pair of the open modular curve inside the compactified modular curve, and that sits in a triangle or in a long exact sequence with this restriction map. Okay? And so really, this is a statement about this relative cohomology. And so what is it? Well, by excision, this is just a sum over the cusps of the relative cohomology of a kind of neighborhood of the cusp and the sort of punctured neighborhood of the cusp. So it's the relative cohomology of like an open complex disk, and with a punctured open complex disk with z mod p to the sc coefficients. Okay? And so now the point is that, okay, I haven't studied algebraic topology in a long time. Probably everyone in this room is better at computing this than me, but I think this is really just the reduced cohomology of a two-sphere, and so it's just it's z mod p to the sc for I equals 2 and 0 for I not equal to 2. Okay? And so now what's the point is that we have to consider the pullback maps when we change the level at P. That was... No. Okay, so now the point is, if I let Kpn be the principal level n congruent subgroup, then the map xkpn plus 1 to xkpn, maybe put in the tame level. So what happens at the cusps? Well, above each cusp, there's many cusps, but they're also, all cusps are ramified with ramification index p. And so this implies that the transition maps on this relative cohomology factor multiplication by p. And so when you take the colimit, there's 0. So basically the same reason that we saw that the completed H2 of the compactified modular curve is 0. Okay, and in the notes you can see a proof from a different point of view that also works for other Shimura varieties. Okay. So the next thing I want to introduce is, I want to pass to analytic geometry and perfectoid geometry and recall how completed cohomology can be computed as pro-étale cohomology of perfectoid Shimura varieties. So I'm going to fix an embedding of the reflex field into QP bar, which gives me a prime of the reflex field. And I'm going to let my coefficient field E be the sort of p-adic completion of the reflex field. And in fact, I'm really just going to go ahead and work over CP, which is going to be the completion of the algebraic closure of E. OK, so now we want to take our Shimura varieties, which are defined as schemes, and turn them into analytic spaces. So I'm going to let more curly S, which I admit is going to often look the same as a Roman X, be this analytification. So we take the algebraic variety, and maybe I will also do this for the toroidal compactification, so either the uncompactified or the toroidal compactification. Okay? So this is just the same thing, but viewed as an analytic space. And so now we want to sort of pass to infinite level at P. And so we can first just define it as a topological space. So let's define the underlying topological space. Sorry, the S is already becoming less curly. Actually, let me just work with the toroidal compactification for now. So we define a topological space for what should be the Shimura variety with sort of infinite level at P and tame level Kp by just taking the limit over Kp of the Shimura varieties at finite level, or the topological spaces underlying them. Okay, and so somehow, I mean, well, I guess what's supposed to be a basic idea of this course is that really this space has kind of multiple incarnations as some kind of geometric object, which corresponds to, oh no, I'm doing the wrong thing, which correspond to somehow different choices of structure sheaf. And so I'm going to define two of them now, and then maybe the third at the end if I have time. So we have sort of two structure sheaves. So the first one, I'm going to call O smooth. And OK, maybe in our notation there's some subscript, but I'm just not going to write it because I don't want to. So O smooth is just the thing that you get by taking the colimit of the structure sheaves at finite level. Or maybe they're pullbacks, but OK. And we call this O smooth because somehow the action of the group GQP is sort of smooth. Any section of this sheaf at infinite level will be pulled back from some finite level, and so it'll be invariant under whatever open compact subgroup was in the level. OK? And then the other one is the sort of p-adically completed version of this. So we're just going to call that O. It's kind of the continuous structure sheaf. So for this, we're going to take the colimit over Kp of the sheaves of bounded elements at finite level. And then we're going to p-adically complete and invert P. OK? And so a priori, this is just a definition, and you maybe can't understand very much about this. But then there's a wonderful theorem of Peter Schulze And maybe I'll sort of state the version. Sorry, there should really be tors everywhere. So I'll state the version for toroidal compactifications, which was proved by Poloni and Stroh. So this is a theorem of Schulze and Poloni-Stroh. The theorem says that, so this topological space together with this sort of completed structure sheaf is a perfectoid space. Okay? And I'll maybe state one more theorem, and so neither of these I'm going to explain much about, which is that, so if we take, so now, I mean, now that we know this is a perfectoid space, we have a theory of étale and pro-étale cohomology, and the theorem says that the étale cohomology with torsion coefficients of the perfectoid Shimura variety, toroidal compactification, is the same as completed cohomology. Okay? Sorry, with z mod p to the sc coefficients. And okay, so just to say in words how you prove this, so I mean, we define completed cohomology as cohomology at finite level of the open Shimura variety. So then we prove that it's really also the completed cohomology of the toroidal compactification, but maybe the étale cohomology of the toroidal compactification as an algebraic variety. Then there's a comparison between étale cohomology of algebraic varieties and étale cohomology of rigid analytic varieties of their analytification. And then you need to explain why this étale cohomology is really the colimit of the étale cohomologies at finite level. And anyways, you can look in the notes. There's some details. Okay, and so let me just say that this has a nice consequence, which is something that was sort of conjectured by Caligari and Emerton, and is, sorry, I really should have, I mean, I didn't write at the beginning of my talk the hypothesis. Let me say if Gx has Hodge type. Sorry, I think I meant to say that at the start of my talk. Then this is a perfectoid space. And we actually don't know this for general Shimura varieties at the moment, but it's believed to be true. So the corollary is that this completed cohomology let's say z mod p to the sc coefficients is 0 for I bigger than the dimension. And this basically follows from this, basically using Schulze's primitive comparison and then vanishing results for coherent cohomology. Okay, it's the sheaf of bounded elements on the analytic space, this thing, yeah. Okay, so in the last 20 minutes of this talk, I need to now tell you something about locally analytic vectors, otherwise Vincent will be very mad at me. So let's turn to that. Okay, no, I still. Oh no. Okay. Okay. The upper right. No, I was using I was pushing the wrong one. Thank you. I thought it was broken. Okay. Okay, so Okay, so maybe some of you have seen this before, and I'm not going to tell you anything you don't know. And so I kind of want to give an explanation of this for people who are maybe not so familiar with this notion. So before I talk about locally analytic vectors, I need to talk about locally analytic functions. So I just want to consider a very simple example. So let's consider functions on ZP. So what does this mean? So a function from ZP, let's just consider QP valued functions, is what I'll call n-analytic. Basically, if on any ball of radius p to the minus n, it's given by an analytic function. So for any x0 in ZP, f of x minus x0 is given by a power series sum an x minus x0 over p to the n, ai to the I, and this is for x minus x0 less than or equal to p to the minus n. And this is supposed to converge on that disk, so these coefficients ai should tend to 0 p-adically. Okay, so n-analytic means that basically on every ball around a point of ZP of radius p to the minus n, it's given by a power series converging on that ball. And so a function is locally analytic if it is n-analytic for some n. And so, in fact, since ZP is compact, it's really the same as saying that for every point, it's given by a power series in some neighborhood of that point, to just say that it's n-analytic at every point for some n. Okay, and so in this way, we get some function spaces. Let me just check. I go to 35, is it right? Yes. Yeah, okay. So we get some function spaces, which I'll call CNN, ZP, QP, and their union, which is CLA, ZP, QP. And so what kind of spaces are these? Well, this is really just a finite collection of power series, right? So this ring of functions is nothing but product over z mod p to the nz of sort of power series, maybe around, of convergent power series in x minus x0 over p to the n. Okay? So in other words, it's just functions on the finitely many Tate disks of radius p to the minus n centered around the points of ZP. Okay, and so in particular, what that means, I mean, coming from this description, we see that the maps CNN, well, so in particular, I mean, this is a Tate algebra, so in particular, it's a QP-Banach space. And the maps where you kind of decrease the radius of analyticity, these maps are compact in the sense defined by Alicia, and in fact, these are exactly the example of the compact maps in Alicia's talk, just restriction from a bigger Tate disk to a smaller Tate disk. And so when we pass to the limit, this function space, CLA ZPQP, is a colimit over compact maps of Banach spaces, and there's some name in p-adic functional analysis. This is an LB space of compact type. Okay, so anyways, it has some topology. Okay, and so like with continuous functions, we could consider measures. With locally analytic functions, we can also consider some kind of distributions. And so let me just sort of briefly say how this works, because I need to start talking about representations, but I think it's sort of at least somewhat enlightening. So we have sort of the bigger function space of continuous functions from ZP to QP, and sort of inside that we have the locally analytic functions. And if we take their duals, so we said before that this is the space of measures on ZP. So in other words, it's the Iwasawa algebra with P inverted. And this is just going to be, by definition, the space of locally analytic distributions, which can somehow be defined as a sort of inverse limit of the duals of these spaces. And so this is, well, I should say what kind of space it is. This is a Frechet space. Even a Frechet space of compact type, or a nuclear Frechet space, or whatever. And so in p-adic Fourier theory, we give some kind of more concrete description of these two rings. And let me just sort of recall that without too much explanation. So actually, Alicia already explained what is this. So this is just, can be viewed as a, sorry. So the Iwasawa algebra is just a power series ring and some variable, which has some meaning, with P inverted. And by the theory of Mies transform, this turns out to be, so I should have written that this is included in this. This is something like the ring of functions, the ring of rigid analytic functions on the open Tate disk of radius less than 1. And so in particular, this ring, it's sort of bigger than this ring. This ring is the ring of bounded functions in this ring. Okay? But this map is still a very nice map. It's faithfully flat, for example. Okay. Okay, that's fine. Okay, so now I want to explain what are locally analytic vectors and representations. And so, I mean, basically the idea is where, I mean, the locally analytic vectors in a representation are sort of the vectors where the action is given by locally analytic functions. Okay, so let's since I don't have a huge amount of time, let me just actually specialize to the case of GL2. And anyways, really, it's what we're going to talk about, and you can guess what the definitions are in general. So the first thing I want to do is I want to consider what I'll call Gn, which is the sort of athenoid analytic group of elements in GL2, which are 1 mod p to the n. And so, I mean, concretely, this is basically just a 4-dimensional Tate polydisk where you can imagine that the entries are just like 1 plus x, y, z, 1 plus w, where x, y, z, and w have radius less than p to the n, or all of them. Okay, and I'm going to let kpn, so this is the group of QP points, be the QP points of this, which is just the sort of principal congruent subgroup. So matrices of the form 1 plus p to the n zp, p to the n zp, p to the n zp, 1 plus p to the n zp. Okay? Okay, so now let V be a QP-Banach representation of one of these groups, Kpn. Okay, so we consider the following thing, which is called the orbit map. And so this is the map which sends V to continuous functions from Kpn to V, which is really just the same thing as the sort of completed tensor product Kpn with valued in QP with V. Sorry, question? No? Okay. So this is a p-adic Banach space. I'm just saying that continuous functions on this profinite set valued in a Banach space is again a Banach space. And this map, it sends, well, a vector V to the function which sends an element g of Kpn to its orbit. Okay? Okay, and so Kpn acts on this sort of space. By, well, okay, it acts maybe in multiple ways, and we need to take the correct action. So we want to take the action which will leave orbits of elements of V invariant. And so that's the following action. So K will act, or maybe let me call it G. G will act on a function in here, F, evaluated on G prime as G, F, G inverse, G prime. Okay? And so the point of considering this action is that if you think about what it means to be invariant under this action, it's exactly saying that you are an orbit of an element of V. So in other words, the invariants are just V. Okay? And so now the idea is that we can impose some condition on vectors by sort of asking that the functions here are not just continuous functions, but something like analytic functions. Sorry, I realized that was a mistake. But now you can see it again. Okay. So the definition is that the Kpn n, well, let me just call it the n analytic vectors. But the n analytic vector, so the n analytic vectors are going to be, well, we basically we replace this function space with the ring of analytic functions. So we take the analytic functions on this group Gn, which I remind you is really something like just a ring of convergent power series in several variables. And take a completed, so it's again a Banach space. So again, we take this completed tensor product, and then we take the, okay, I realize I've been doing something slightly wrong. I should really be, sorry, but I should really be letting this n be a different n. So, okay, well, actually, it doesn't really matter because it's the same thing if you just restrict to that bigger n, but okay. Okay. And what do I want to say next? Yeah. KPN prime. Yeah, sorry, I should have just written n's everywhere, but it doesn't really matter. But I mean, okay, the reason I wanted to write it like this is that now we take, so the locally analytic vectors to just be the colimit over sort of n prime of the n prime analytic vectors. And I guess the thing I wanted to say, or the reason I said this in this silly way, is that this really has an action of Kpn. Okay, and so what kind of spaces are these? So again, this is going to be a Banach space. And this is going to be a colimit of Banach spaces. This is a LB space. And it will be of compact type if V is admissible. Yeah, so sorry, I started with a representation of Kpn. Yeah, I shouldn't have done that, but yeah. So I'm defining the n prime analytic vectors in a representation of Kpn. Okay, and basically, well, maybe I don't really have time to explain this, but basically it reduces to the case of the sort of primordial example of an admissible representation, which is just the continuous functions. And if you think about what this is in this case, or in particular in the case that this Kpn is actually Zp, so the example I started with originally, you'll exactly recover the space of n analytic functions. And so the transition maps will be compact in that case. Okay. Yeah. Yeah, so I'm about to say that. Yeah. Okay. Okay, and maybe before I say the thing that Joaquin wanted me to say is that let me just say that, okay, so if V is a sort of QP Banach representation of GQP, so in particular we can restrict it to Kpn or Kp1 or whatever, and apply this formalism, but the locally analytic vectors has an action of GQP. And maybe I don't really explain this, but the point is that if you take an element of GQP, it will sort of conjugate this principal congruent subgroup to some conjugate, but then that will contain one of the smaller congruent subgroups. And so you really get an action on the locally analytic vectors, but of course not on the n analytic vectors for any n. Okay, and just to finish, I want to recall theorem of Schneider and Teitelbaum. says so the following. So sort of on category of admissible representations of KPN, V mapping to VLA is exact, and VLA being 0 implies that V is 0. So local analytic vectors kind of don't forget anything in some sense. At least, yeah. And so, okay, I'm not really going to explain the proof of this. I also have like 0 time. But the idea is that, again, you pass to the dual side. Oh, okay, so it's not a proof. You sort of pass to the dual side, and you use that this map from measures to locally analytic distributions. Well, I only define this for ZP, but the definition is exactly the same for any compact p-adic manifold, is faithfully flat. And I explained what this map looks like in one case. And anyways, that's something that really has to be proved. Anyways, that's the idea of how this theorem is proved, and I stop.